share the screen. Takes time. Okay. So we start talking about the MOS capacitor. I'm sure that you know already what the MOS capacitor is, anyhow. Okay, there we are. So the MOS capacitor is a structure that is made of a silicon substrate on which a layer of insulator is deposited or grown. In the silicon technology, the insulator is typically made of silicon dioxide, SiO2, and this layer is obtained by growing the oxide on the silicon, by exposing silicon at high temperature to a gas in which there is some concentration of oxygen. If the insulator layer is made of some other material, then it is deposited. It is formed beforehand and then deposited on top of the silicon layer. Then a metal contact is deposited on top of the insulator, and another contact is deposited on the other side, on the semiconductor. So we have a sandwich that is made. If you look at the figure and you start looking at the figure from the left, you have a metal layer. It is indicated with metal here. The thick vertical line is the interface between the metal layer on the left and the insulator. Then we have the insulator as indicated here at the bottom. The other thick vertical line is the interface between the insulator and the semiconductor. And finally, we have the semiconductor. If you go further to the right, at some point you end up meeting the other contact. The other contact is not indicated in this figure, but it does exist. It is on the right. In this figure, we assume that the semiconductor is uniformly doped with an acceptor dopant concentration. So you remember if you look at the position of the Fermi level, E sub f, you have the upper edge of the valence band below. Then you have the lower edge of the conduction band above. Then the dashed line is the position of the mid gap that coincides, as you remember, with the almost coincides with the intrinsic Fermi level that is indicated here as EFI. And then since the dopant is of the acceptor type, the Fermi level of the material is below the intrinsic level, E sub f. Be careful because this diagram mixes energies and potentials. So you remember that the potential energy for the electron is minus Q times phi. Phi is the electric potential. That means that the orientation of the energy axis is opposite to the orientation of the electric potential. So as usual, in this figure, we take the orientation of the energy axis bottom up. So you see here that the energy axis points upwards. So in this figure, the electric potential has the axis that points downward. Okay, so it grows when we go lower in the figure. Okay. Of course, the structure is one-dimensional, so we assume x-axis is aligned, is horizontal, okay, normal to the interfaces. And we assume that we are applying a constant voltage between the metal on the left and the metal on the right. The metal on the left is also the metal contact on the left is also called the gate contact, as you know very well. And the contact on the semiconductor that is on the right in this figure is called the bulk contact. So we apply some voltage that we call Vg, V sub G, between the gate contact and the bulk contact. And we assume that this voltage is constant with respect to time. Now, the point is that we have an insulator in the structure. So not only we have an insulator, if the insulator is silicon dioxide, it is one of the best insulators that are available. So when we apply a constant voltage, no current can flow through the device. So the current is zero and the device is in the equilibrium condition, okay? So as long as the applied voltage is constant with respect to time, the structure is in the equilibrium condition, so it is sufficient out of the mathematical model of semiconductor devices, it is sufficient to use the Poisson equation only to study the behavior of the device. It is convenient when we study the MOS capacitor by itself, not as a component in a larger circuit. It is convenient to set the zero of the electric potential asymptotically in the semiconductor, as we used to do in the PN junction or in the transistor. You remember, we always take the zero inside. So the assumption for the moment is that the zero of the electric potential coincides with the horizontal part of the dashed line, that is the mid gap, okay, on the right part of the figure. This line is also continued by the continuous line on the left. So the continuous line on the left, that I'm indicating now with the mouse, is the reference of the electric potential. It is the zero of the electric potential. So when we apply a voltage that we call VG between the gate contact and the bulk contact, then we must remember that when we are in the bulk contact and we enter the semiconductor from the right into the semiconductor, you remember when there is a contact, we have a discontinuity in the electric potential that we already mentioned, for instance, in the PN junction, and we call the difference in the work functions of the metal and the semiconductor. Okay? That means that the electric potential inside the metal of the bulk contact, but outside of the semiconductor, differs by a constant with respect to the electric potential inside the semiconductor asymptotically to the right. Okay? So we have to account for the difference. It is easy. At some point we shall introduce this difference, but for the moment, since we are not considering the bulk contact, we must observe that the difference in the electric potential between the left contact, that is the gate contact, and the internal zero of the potential is different from VG, because we are using as a reference the interior of the semiconductor. So for this reason, we use another symbol. This symbol is indicated here, VG prime, is the difference between the contact, the gate contact electric potential, that is the horizontal line that I'm cutting now with the mouse, and the internal zero of the electric potential. Obviously, VG prime differs by a constant with respect to VG, that is the actual voltage difference between the two metal contacts. And this difference is indeed the difference in the work function that we mentioned earlier. Now, it is qualitatively straightforward to study the behavior of the electric potential in the structure. If we start from the metal and we apply some VG prime, as in the figure, you remember metals are equipotential in the interior, okay, because there is no charge density different from zero inside the metal. So the potential is constant and equal to VG prime inside the metal. Then we enter the insulator. We assume that the insulator is perfect, so there are no charges inside the insulator. In reality, during the fabrication process, it may happen that some unwanted charge enters the insulator and then it stays there as a fixed charge, okay? But we assume that there are no such charges, okay? So the insulator is a one-dimensional region free of charge. So when we solve the Poisson equation in the insulator, we have simply that the second derivative of the electric potential is zero because there are no charges inside the insulator, okay? Since the second derivative is zero, it follows that the electric potential inside the insulator is linear. So we have a linear behavior of the electric potential. You see that we have an angle when we cross the interface between metal and insulator, okay? So the angle means that the electric field is discontinuous. The electric field, in fact, is zero on the left because the metal is equipotential, and is non-zero on the right. The reason that we shall see in a minute is that there is a layer of charge at the interface on the side of the metal. Then we continue. The potential is linear inside the insulator, and at some point we reach the position of the interface between the insulator and the semiconductor. And at that point, the electric potential has some value that we don't know yet, but this value is important. It is the value of the electric potential at the interface between the insulator and the semiconductor. This potential is important. It takes a special name. It is called the surface potential. And the symbol, as you see in the figure, is phi s. Then we enter the semiconductor. The electric potential is continuous at the interface between insulator and semiconductor because we don't have any double layer of charge. But the electric field is discontinuous. So the slope, it is not very visible in the figure, but the slope on the left and on the right is different here, okay? What happens in the semiconductor? Well, it depends on the value and sign of the applied bias. In the case of the figure, that is one of the possible cases, of course, Vg prime is positive because you remember we anticipated that the positive direction of the axis for the electric potential points downwards. So we have a positive voltage applied on a structure in which the semiconductor is of the p-type. So the p-type means that the semiconductor is very rich of holes and poor of electrons. Okay, so qualitatively, in this case, we expect that the application of a positive voltage on the left will push the holes away from the surface, from the interface between insulator and semiconductor. So the holes will go to the right, and they will leave behind a region in which the holes have left, so to speak. The electrons are not so many because the material is of the p-type. So there is a region in which qualitatively the most important contribution to the charge density is given by the acceptor atoms. Okay, so we have a region in which the charge density essentially is equal to minus Q and A. Okay, it's like on one of the two sides of a p-n junction biased in reverse. So this applies to the example in which Vg prime is positive and the substrate of the semiconductor is p-doped, okay? So in essence, we have formed a space charge region. But if you go far away from the surface, we expect that sooner or later the semiconductor will not anymore be influenced by the situation near the interface. So far away from the interface, the semiconductor will behave like a uniformly doped semiconductor. So essentially it will be neutral. So qualitatively, in this example, we can distinguish in the semiconductor two regions. A neutral region that is on the right of the vertical dashed line here. And in the neutral region, essentially, the electric potential is constant. So it is an equipotential region. The electric field is zero. Okay, and the concentration of the electrons and holes is also constant. And then we have a space charge region here, which is substantially depleted of holes, and there are not so many electrons. So in this respect, the situation is similar to that of on one of the two sides of a p-n junction. But there is a difference that since we have applied a positive voltage to the gate, this positive voltage not only will push the holes of the semiconductor to the right, but will also attract the electrons of the semiconductor to the left. But these electrons may travel up to the interface. When they have reached the interface, then they cannot proceed anymore because there is an insulator. So in the situation illustrated in this figure, we have a layer of electrons at the surface, at the interface between insulator and semiconductor. Of course, they are on the semiconductor side. Okay, so we can illustrate the distribution of the charge schematically. Of course, it is very schematic, okay? As shown in the lower part of the figure, don't mind about these indications SIL1, SIL2, and SIL3, okay? They are used for some calculations. In this condition, if you look at the vertical dashed line that separates the space charge region on the left from the neutral region on the right, okay, you have that from the surface to this vertical dashed region, essentially we have a uniform concentration of charge that is fixed and due to the dopants, exactly as we did on the p side of the p-n junction. So we have a depleted region whose extension we call LP, as we did in the p-n region, in which the constant charge density is minus QNA. Na is the concentration, is the density of the dopants of the acceptor type. And if we also use remember the Ashe approximation, the abrupt space charge edge approximation, we assume that there is a discontinuity of charge. We go abruptly from the space charge region where the concentration of charge is a non-zero constant, okay, to the neutral region where it is zero. In addition to that, we have a layer of electrons. Of course, the space charge region is negative because it is due to acceptor, it is minus QNA. Then we have a layer of electrons that is much thinner than LP, And the layer of electrons produces another contribution to the negative charge that is very close to the interface. And it is represented by this box here near the interface, okay? So by applying a positive charge, a positive bias, sorry, on the gate, we have negative charges in the semiconductor. The total of them is the sum of those due to the electrons of the layer plus those due to the dopants, okay? On the other hand, globally, the device is electrically neutral. So if we have an excess negative charge on this side, we must have an excess positive charge on the other side, that is on the side of the metal, okay? Now, you remember, metals are equipotential regions, so it is forbidden, so to speak, for a metal to have a non-zero charge density in the interior. So if a metal is electrically charged, the only possibility is that the charge stays at the boundary. And in this case, the boundary of the metal is the interface between the metal and the insulator. So we have a positive charge, a positive layer of charge whose thickness is very small. And it is depicted as this stick here, okay? And the area of this stick should be equal to the total area of the negative charges, because the positive charge in the metal is equal and opposite to the total negative charge in the semiconductor, okay? So what happens in reality when we apply a positive voltage to the gate? We start from equilibrium. So there is no charge nowhere. Everything is neutral everywhere in the structure. Then we apply a positive charge here, okay? We simply push electrons away from the metal into the semiconductor, okay? So we have an excess negative charge in the semiconductor, and we have a missing negative charge in the metal that is equivalent to a positive charge at the boundary, okay? Another symbol that is important here is the thickness of the insulator that is indicated, as you see at the bottom of the figure, with Tox. T stands for thickness, ox because we imply that the insulator is made of silicon oxide, okay? Now, it is very easy to find quantitative relations among these charges, okay? For the moment, we give some numbers. The thickness of the metal layer, of the charge layer on the metal side, this one, is a few angstroms. So say 5 angstrom, okay? The thickness, so it is obvious that when we have to deal with the charge in the metal, we mathematically consider it as a Dirac delta, okay? The layer of electrons in the semiconductor, if it exists, because it exists here because we apply the large positive voltage to the gate, okay? If it exists, the thickness of the layer at the interface is about 10 times larger than that on the metal side. So it could be 50 angstroms, okay? But yet in some simplified calculation, we can consider also this layer as a Dirac delta. LP, you remember, can be some microns, okay? Is the typical width of the depleted region, okay? So in order to obtain quantitative relations between among these quantities, we simply apply the Gauss theorem, okay? Because we are in a static situation, so it is sufficient to apply the Gauss theorem that is somewhat equivalent to the Poisson equation, to integrating the Poisson equation once. So you remember that the Gauss theorem states that if you take any volume and then integrate the flux of if you calculate the flux of the displacement vector over the surface of this volume, you obtain the total charge inside the volume itself. So we simply take three volumes of cylindrical form, and they are cylinder 1, cylinder 2, and cylinder 3 that are indicated in the figure. So the axis of each cylinder is horizontal, it's parallel to the x-axis. Each cylinder has two lateral faces, one on the left and the other on the right. And then there is the lateral surface of the cylinder. But of course, here we are in the one-dimensional case. So the only non-zero components of the displacement vector are those that are horizontal. That means that the left face and the right face of each cylinder contribute, or may be able to contribute, to the Gauss theorem. The lateral surface of the cylinders does not contribute, so we don't consider it, okay? So in essence, we take the first cylinder with the left face inside the metal, okay? So remember the displacement vector is proportional to the electric field. So the electric field normal to the left face of cylinder 1 is 0. Instead, we take the right face of cylinder 1 inside the oxide. So inside the oxide, you see the potential, the electric potential is linear. That means that the electric field is constant because it is minus the derivative, okay? So we place the right face of cylinder 1 anywhere inside the insulator. That means that the displacement vector will be the dielectric constant of the insulator times the electric field inside the insulator. Next, we take cylinder 2. Cylinder 2 has the left face inside the oxide, whereas the right face is inside the semiconductor, but very, very close to the interface. So why do we take it very close to the interface? Because we don't want any charge in this cylinder, okay? So if we take the cylinder with the right face as close as we please to the interface, the amount of charge in the cylinder will be 0. There is no charge on the oxide side, okay? And the charge inside cylinder 2, to the portion of it belonging to the semiconductor, will be negligible. But on the other hand, since the right face of cylinder 2 is inside the semiconductor, we shall use the permittivity of the semiconductor. And finally, we take cylinder number 3, again with the left face, in this case, very close to the interface, but inside the semiconductor, and the right face far away in the bulk, where the semiconductor is equipotential, so we don't have any field, okay? So only the left face of cylinder number 3 would contribute to the Gauss theorem, but cylinder 3 is big enough to contain all charges that are present in the semiconductor, okay? Since we have a one-dimensional case, after the calculation, we can divide all the results by the cross-sectional area of the cylinders. This area is normal to the page, okay? So that instead of considering the charge, we shall consider the charge per unit area in each cylinder, okay? Now, the application of the Gauss theorem in one dimension is very easy, okay? And before we proceed with this application, we just define some quantities. If you look at the first line, if you indicate with rho sub m, you see it on the left, the density of charge of the metal, of course, rho sub m is simply the little stick near the interface, okay? And you integrate it over the extension of the metal, that means between minus infinity and minus T ox. Oh, by the way, we place the origin of the X reference at the interface between insulator and semiconductor. Okay, that is the origin. So the position of the other interface between the metal and the insulator is minus T ox. Okay, so the integral of the charge density rho m over the metal gives you the charge per unit area of the metal. We call it capital Q sub m. Then we do the same for the oxide. So if we integrate rho sub ox, that is the charge density inside the oxide, over the extension of the oxide, we obtain Q sub ox, okay? And this is the charge per unit area in the oxide. And in this analysis, we assume that it is 0. Rho ox is 0. Finally, the charge per unit area of the semiconductor will, of course, be defined as the integral between 0 and infinity of rho, where rho is the charge density of the semiconductor, okay? Then we can approximate the charge density in the metal as a Dirac delta. So you see the second line shows that rho m is proportional to the Dirac delta centered at minus T ox. So it is a delta of x plus T ox. Then we have to multiply by Qm, because you remember, if you integrate the delta, you obtain 1. Okay, so if you integrate rho m, you must obtain Qm. And then you add a factor of 2, because actually this delta is centered at minus T ox, but in the integration, you take only 1/2 of it, because you take the half, so to speak, of the delta, of the Dirac delta that is on the left of the interface, okay? Not that is on the right, because there is no charge in the oxide, okay? So since you take 1/2 of the delta, you must multiply by 2 in order to have the correct charge density. Next, we take the charge density in the oxide equal to 0, okay? You remember we already made this assumption, and for this reason we concluded that the electric potential is linear in the insulator. At this point, it is very easy to calculate the electric field inside the oxide, because since the potential is linear, then the electric field is a constant, and you see immediately from the figure that you must take minus the derivative of this line. So it is phi s minus Vg prime divided by Tox with a minus. Okay, so when there are no charges in the oxide, the oxide field is this one, Vg prime minus phi s over Tox. And finally, so all of this makes it trivial to make the calculations in the metal and in the insulator, okay? Instead, the charge in the semiconductor, well, we are in the equilibrium condition. As usual, we make the assumption that the semiconductor is non-degenerate, so we can use the exponential expressions for the concentrations, and that we are in the complete ionization condition, okay? That means that the net dopant concentration N is actually equal to minus NA. It's a constant, okay? So the expression of rho is Q times, you are accustomed to this, P up 0 exponential of minus Q phi over KT. Then we have the electrons minus N up 0 exponential of Q phi over KT, okay? You remember that P up 0 and N up 0 are the values of the concentrations where we have taken the 0 of the electric potential, that in this case is in the asymptotic region of the semiconductor. The semiconductor is of the P type, so P up 0 is actually PP0, you remember the symbol, and N up 0 is NP0, okay? Then we have the Gauss theorem, okay? It's really trivial. If you apply the Gauss theorem to any of those cylinders, and you remember that only the two faces contribute, then the final relation is this: the displacement vector on the right face, that we call d right, minus the displacement vector on the left face. Of course, d is the component parallel to the x-axis, that is the only component that exists in this problem, is equal to q, that is the charge per unit area of the cylinder, okay? So from our analysis, we can conclude that the left contribution, the contribution of the left face to the displacement vector, you remember, is for cylinder 1 is dm equal to 0 because we are in the metal. For cylinder 2, it is, we call it dox, is the product of the permittivity of the oxide and the electric field in the oxide. And for cylinder number 3, it is the displacement vector at the interface between insulator and semiconductor, but on the semiconductor side. So this is the origin of O plus, of 0 plus, sorry. And this is equal to the semiconductor permittivity to the surface field in the semiconductor. So the surface field in the semiconductor is the electric field that corresponds to this point here, but on the side of the semiconductor. So it is the slope of the dashed line here calculated in the origin. This is for the left, for the contribution of the left phase of cylinder 1, 2, and 3. Now we go to the right phase. The right phase is, of course, for cylinder 1, we are inside the insulator. So again, it is the oxide permittivity times the field EOX. For the second cylinder, we are in the vicinity of the origin on the semiconductor side. So it is permittivity of the semiconductor times the surface field. And finally, we go to infinity for the right face of the third cylinder. Okay? So we have to replace one by one the first line, the second line, the third line at the left-hand side of this relation here, d right minus d left. Then we have Q. Q is the charge in the metal for the first cylinder, the charge in the oxide, that is 0 for the second cylinder, and finally the charge in the semiconductor, QSC, for the third cylinder. So when we put this thing together, so when we impose this equality here for cylinder number 1, 2, and 3, we obtain this relation for cylinder 1, this relation for cylinder 2, and this relation for cylinder number 3, okay? Of course, they are not independent. You see that QM is equal to this, which is also equal to this, which is also equal to this, which is equal to minus this, which is equal to minus this. So by combining this relation, we obviously obtain that the total charge per unit area that is present inside the semiconductor is equal and opposite to the total charge per unit area inside the metal, okay? By the way, the example of the figure was taken for a positive value of the applied voltage to the gate contact, okay? But this calculation here is general. We did not make any assumption about the value or the sign of the applied voltage. So this is fully general, okay? Fully general. The only assumption is that there are no charges in the oxide, but this is very reasonable. Before we close, there is another observation. You see that the relation here, the second relation here, provides a relation between the value of the field in the semiconductor at the surface and the field in the insulator, okay? And these two values of the field are in the inverse ratio as the dielectric constants of the two materials, okay? If you consider silicon, the dielectric constant of silicon is almost exactly 3 times larger as the dielectric constant of the silicon dioxide. So the surface field on the semiconductor side is almost exactly 3 times smaller than the oxide on the other side. So we have a discontinuity of the normal component of the electric field that is due practically only to the difference in the dielectric constants because there are no charges around in this calculation, okay, near the surface. So we stop now for about 10 minutes and then we resume at 4:40. Okay, so we restart. Let me put the figure, the page back. Okay, so we have found a relation that is quite reasonable. That is the charge per unit area in the metal is equal and opposite to that in the semiconductor. And then we can also put together other relations that are of importance. For instance, if you consider the relation that provides the electric field in the insulator, this one, and you multiply both sides by the permittivity of the oxide, then the left-hand side will be Qm, okay? So we have an expression of Qm in terms of the applied voltage and of the surface potential. And of course, considering that Qm is opposite to QSC, to the semiconductor charge, then we have the expression of the semiconductor charge in terms of other quantities. So we do it. The semiconductor charge is minus per unit area, is minus the metal charge per unit area. We replace the expression of Qm as minus E epsilon ox E ox, and then we replace the expression of the insulator field. We notice immediately that we have the relation of the two constants, epsilon ox divided by the oxide thickness, okay? You remember when you have a parallel plate capacitor, the capacitance of it is equal to the permittivity of the dielectric times the area of the capacitor divided by the thickness of the dielectric. If you don't have the area or you divide by the area, you obtain the capacitance per unit area. So the ratio of epsilon ox over T ox is nothing else than the capacitance per unit area of the oxide, okay? So if you use this definition, we have a very compact relation that connects the charge in the semiconductor per unit area to the surface potential, okay? The other quantities are given. Vg prime is given because it is the applied voltage, and the capacitance per unit area is also given, okay? Is this expression sufficient? Well, no, because in this expression we have two things, that is the charge and the surface potential that are unknown, so it is still insufficient. It is very good, very compact, okay, very simple, but insufficient in itself to give us the values of phi s and QSC, okay? So we need another relation, okay? But we do have another relation. So this relation here, QSC as a function of phi s Vg prime that we have just found is one of them, okay? The other relation is the second one, QSC equal to minus the permittivity of the semiconductor times the surface field in the semiconductor, okay? So this is another relation that we found by using the Gauss theorem on the cylinder number 3, the one that is in the semiconductor, okay? Does it solve the problem? Not yet, because yes, we have another relation, but we have another unknown that is the surface field, okay? But as we shall see in a minute, if we solve the Poisson equation in the semiconductor, which we did not do yet, we can find a relation between the surface field and the surface potential. So actually, at the end of the calculation that we are going to perform in a minute, we shall have two relations. One is the original one, this one with the capacitance, okay, that relates QSC with phi s and Vg prime. And the other one is QSC as a function of phi s. Okay, so by eliminating QSC, we of course eventually will be able to calculate the value of the surface potential for a given applied voltage. So we have solved, so to speak, the structure, because after we find the surface potential, we can go back and reconstruct QSC, the charges, whatever, okay? So the issue now is solving the Poisson equation in the semiconductor. It is not so difficult because we know the expression of the charge density in the semiconductor. Remember, before we continue, we must introduce some useful definitions. First of all, we observe that we have a one-dimensional problem only. Okay, so the only dependence is on the x-coordinate. The second property, very important, is that the dopant concentration is constant with respect to space. Okay, actually in this case it is equal to minus Na, that is the acceptor concentration. Then the Poisson equation is a differential equation of the second order, so we need two boundary conditions or two initial conditions. But we know them because we know that if we go asymptotically to the right, the semiconductor becomes equipotential. So first of all, the field at infinity is zero because the semiconductor is equipotential. And number two, we have placed the zero of the potential at infinity. So the two conditions are that phi at infinity is zero and phi prime at infinity is also zero. Then you remember that P up zero is actually P at infinity because it is we take the zero of the potential at infinity. So P up zero is PP zero, which is substantially equal to NA. And N at infinity is NP zero, it is Ni squared over Na. Then we introduce, for convenience, the normalized electric potential. So instead of using phi as the unknown function, we use the normalized potential that is Q phi over KT. And then we introduce a parameter LA that is a length. This length is called the dBi length for the holes. And its definition is, as you can see in the page, is the square root of 2 times the permittivity of the semiconductor times KT divided by Q squared PP0. Now we can express the charge density using the new symbols. So instead of P up 0, we use PP0. Instead of N up 0, we use NP0. And instead of Q phi over KT, we use the normalized potential U. Then we can find another relation. The other relation is quite simple. If you observe that when you go at infinity, u becomes equal to 0 because we have placed the 0 of the potential at infinity. So rho at infinity is equal to Q times PP0 minus NP0 plus N. But this quantity also must be equal to 0 because the semiconductor at infinity is neutral. So rho at infinity is equal to 0. That means that PP0 minus NP0 plus N is also 0. That means that N can be written as NP0 minus PP0. So we replace N in this parenthesis that I'm marking now here with this expression. Then we extract a minus from the expression of rho, and we also extract PP0, okay? So after this is a simple algebraic manipulation. We can express rho as minus QPP0 times a function A that depends on U. And this function is here. A of U is equal to the ratio NP0 over PP0 times exponential of U minus 1. And then we have plus 1 minus exponential of minus U. So A, this function A has some properties. First of all, it is dimensionless, okay? It's a pure number. Number two, when U is 0, A is also 0, obviously, because the exponential become equal to 1. Then, when U is positive, then A is also positive, because exponential of U is larger than 1 and exponential of minus U is smaller than 1. And finally, when A is negative, when U is negative, A is negative. So this function has no dimensions and has the same sign as the argument U. Also, we notice that the coefficient NP0 over PP0 is very small, okay? You can write it as, if you replace NP0 with Ni squared over Na, this ratio NP0 over PP0 can also be written as Ni over Na squared. So it is a very, very small number, like 10 to the minus 12 or so. Okay. And it can also be recast as exponential of minus 2f. Okay. UF is not defined, but UF is the normalized Fermi potential. So it is phi f times Q over KT. Okay. Now we have all the ingredients for putting the Poisson equation together in normalized form. So we start with the general form. This is the first of a Maxwell equation, okay, in which we have replaced the electric field with minus the gradient of phi. So this is the Poisson equation in 3 dimensions and in the non-normalized variables, okay? If you do it in 1 dimension and you replace the symbols, you find this equation. It's the second derivative of U with respect to x equal to 2 over the square of the Debye length times this function a of u. Okay, so this is a second order differential equation, which is of course non-linear because a depends on the unknown u through the exponentials. Exponential of u, exponential of minus u. Okay, so it looks ugly, but it is not so ugly because this equation has a special property that nowhere in the equation we have an explicit dependence on x. Okay, you see the right hand side depends only on u. There is no explicit x because the dopant concentration is constant, does not depend on position. Okay, this is very convenient. So you may remember from calculus that we have a trick for solving this equation. Okay, and the trick is one possibility is that u is everywhere equal to 0. Okay, this is the trivial solution. Okay, obviously if u is everywhere equal to 0, then this is a possible solution of the equation. If we discard the trivial solution, we must assume that u is non-zero. Okay, but u is 0 at the boundary. So if it is non-zero elsewhere, that means that the first derivative is non-zero as well. Okay, so we may assume that the first derivative of u, that is the normalized electric field, is non-zero, and then we multiply by u prime both sides of the equation, and this is the trick for solving the equation. Why? Because when you multiply by u prime, the left-hand side becomes u prime u second, or u prime prime, okay? And you see immediately that u prime prime is just 1/2 the derivative of u prime squared. So we have transformed the left-hand side into a derivative. So this is obviously integrable, okay? The right-hand side becomes 2 over LA squared times A times U prime. And this is also integrable immediately, as we shall see in the next page, okay? So by this trick, multiplication by U prime, solving the equation at least once is an easy method. So we just integrate both sides from infinity to 0, okay? Before we do that, you see this 2 factor here goes there and becomes 4. So we have that the left-hand side is the derivative of u prime squared integrated over x between infinity and 0. This is obviously u prime squared, okay? And when u prime squared is considered at infinity, u prime is the electric field apart from the factor kT over Q, okay? So u prime is like the electric field, okay? When we are at infinity, the electric field is 0. So we change the variable from x to u prime squared. And when we go to infinity, u prime is 0. When we go to 0, that is to the interface, u prime becomes u prime of the interface. We call it u prime s. Okay? So we continue to the third equation. This, of course, is equal to u prime s squared, but u prime is the normalized field. normalized with respect to Q over KT. So if we then go to the non-normalized symbols, US prime squared is equal to Q over KT times the surface field squared. Of course, when you go from the potential to the field, you have a minus, but you have a square. So the minus is cancelled by squaring, okay? So the left-hand side is done. The right-hand side is the integral from infinity to 0 of a of u prime dx. But of course, u prime dx is du. So again, we change the variable, in this case from x to u, and the integration limits become, at infinity, u is 0, because as you remember, we place the 0 at infinity. And at the surface, u becomes the normalized electric potential. We call it US, okay? So this function is a function of u that is very easily integrated with respect to u, because the only thing that we have to do is to integrate. The exponential of u integrated is again the exponential of u. This one integrated with respect to u gives you a u. Again, this one gives you u, and this exponential gives you exponential of minus u with the minus. Okay, so the integration of a sub u of a of u with respect to u is trivial. Then you remember that we had a discussion about the properties of a. Okay, a is positive when u is positive. A is 0 when u is 0. A is negative when u is negative. Okay, now we exploit this property. Okay, and we can find immediately that if US is 0, of course, this integral is 0. Okay, because both limits are 0. If US is non-zero, the integral is strictly positive because of the properties of u. Okay, so since the integral is never negative, we can call it f squared. Okay, because it can be demonstrated because of the properties of a that the integral is never negative. Okay, so this integral will depend, of course, on two quantities. One is US, and the other is UF, because this coefficient can be expressed as exponential of minus UF. What is this function f squared here? Well, you simply integrate here and you find it. Okay, so f squared is equal to exponential of minus 2 times UF. That multiplies exponential of US minus 1 minus US, plus another term, exponential of minus US minus 1 plus US. Okay, so f can be expressed as a function of the surface potential. And you see on the left we have the electric field at the surface only. So by this expression we can express the electric field at the surface as a function of the surface potential. So we have completed, we've accomplished the task that we had to do. At this point we calculate the charge in the semiconductor per unit area, QSC. You remember, it is equal to minus the permittivity times the surface field in the semiconductor. At this point, we extract the surface field from here, When we do it, we have a square, so we have two signs, okay? We have a double sign to be discussed, okay? And then we have some constants times this function f. This f is, of course, the square root of all these expressions in the upper line, okay? Now we have to discuss the sign, but this sign can be discussed easily because if you go back to the figure, you remember when you apply a positive voltage, you have a negative charge in the semiconductor. Also, when you apply a positive voltage, it means that the field at the surface will go from left to right. So it will be positive. Conclusion, when the surface field is positive, the charge in the semiconductor is negative. Of course, when the electric field is zero, the surface potential and the surface are zero. And finally, when the surface potential is negative, the surface electric field is negative and the charge in the semiconductor is positive. So all of this is grouped in this parenthesis. So I repeat it. When the surface potential is positive, the charge in the semiconductor is negative. Intuitively, you can think a positive surface potential attracts electrons, and the electrons are negative. When the surface potential is negative, the charge is positive. A negative potential attracts holes to the surface. Finally, when US is zero, you can look at the function f squared, okay? When US is zero, this exponential is 1 and kills the 1. US is 0. This exponential is again 1 and kills the 1. US is 0. So F is 0 when the surface potential is 0. That makes the field and the charge equal to 0. Okay. Now, surface potential equal to 0 means that in this figure, this value of phi s goes to 0, so it goes up until it reaches this line that is the reference for the 0, okay? When that happens, also the bands become straight, okay? So the curvature of the bands here and there, and also of the dashed line, vanish, okay? So the bands are flat, are fully horizontal everywhere. This condition is called the flat band condition. So US or phi s equal to 0 is called a flat band condition. Okay. Now the question is, what is the applied voltage such that we have the flat band condition? Now, if you consider this relation here, that is fully general, okay? Because it is found by solving or using the Gauss theorem on the side of the metal substantially. Okay, so this is fully general. In the flat band condition, phi s is 0, and also QSC is 0. You have 0 potential, 0 field, 0 charge. That implies that Vg prime must be 0, which is obvious from the figure. Vg prime goes to 0 and drags phi s to 0 as well, okay? But you remember, Vg prime is not the difference in voltage between the gate contact and the bulk contact. Vg prime is equal to Vg apart from a constant, okay? So in order to achieve the flat band condition, we must force Vg prime to be equal to 0. That means we must select the value of the actual gate voltage equal to some constant that is non-zero. And this constant, as you remember from the discussion before, is the difference of the work functions between the semiconductor and the bulk metal. Okay? This constant is, of course, a voltage, is a constant voltage that we call the flat band voltage. So this constant takes a name. We call it VFB. So in conclusion, Vg prime from now on will be Vg minus V of flat band. Okay? You see immediately that this expression that we have just calculated is fully general because we did not introduce any approximations into the problem, but it is also quite inconvenient because this function f is the square root of some function that contains exponentials and algebraic pieces and so on, okay? So we may look deeper into it just to check whether there are limiting cases that are easy to deal with, okay? So a first limiting case that is easily discussed is the case in which US is negative and relatively large in modulus, okay? So if US is a large negative number, the dominant piece in this expression of f squared is the exponential of minus US, okay? Because US is a large negative number, okay? The exponential of US will vanish if US is very negative. Then you have these pieces, but these pieces are multiplied by a very small number. You remember, this is a very small number. And US minus 1 have no deal with respect to the large exponential. So when US is very negative, we can approximate f squared as the exponential of minus US. And if you take the square root, you have minus US over 2. Exponential of minus US over 2. Okay, so this is the first limiting case. The second limiting case is when US is positive and large enough to make this exponential here dominant. Okay, so take US positive and large. So this exponential with the minus becomes vanishing, okay? And assume that this exponential here is large, so that in the square, in the brackets, we can neglect -1 and minus US. So we have just an exponential, okay? But this exponential is multiplied by the other exponential that is outside, and that exponential is very small, okay? But at some point, if US keeps increasing, then US will become larger than UF. And at this point, this exponential will become dominant, regardless of the small factor in front of it, okay? So if US is larger than UF, 2UF, then this first part of the function dominates. Then we take the square root, and the function is proportional to the exponential of US divided by 2 times the square root of e to the minus 2 UF, that can be written, as you remember, in this form, okay? And then we have the intermediate situation in which US is positive but not enough to make the exponential of US to dominate. So maybe the other pieces will be dominant. So if US is in between 0 and 2UF, the exponential with the minus will be small. We neglect it, okay? The exponential with the positive sign will be large, but not enough, because it is multiplied by a small number, okay? So all the first piece is negligible. So we are left with US minus 1 that we can further approximate with US. So in the intermediate region, F squared behaves like US, so F behaves like the square root of US. There is a diagram here. Let's make it smaller. It is given in normalized form. So the horizontal axis has US over UF as unknown. So remember, when US is larger than 2UF, that means that this ratio is larger than 2, okay? This is, of course, a log scale, okay? So the vertical axis is in the log scale. So the straight line is an exponential, that is the exponential of US over 2 times this constant that applies for US larger than UF. Then we have the negative values. Again, you have another exponential with a slope that is minus US divided by 2. And then you have the region in between, in which qualitatively you can see a behavior like that of a square root, okay? Of course, in a log scale, when the charge is 0, the diagram goes to minus infinity. So this peak here is because we are in a log scale, okay? So this is the behavior of the charge per unit area in a log scale as a function of the normalized potential. We can distinguish at this point different regions, okay? One was already discussed. It is the region for negative US. Then we have the value of US equal to 0. That is the flat band, where we have the charge in the semiconductor equal to 0. Then we have the values larger than 2 UF. And then we have the region in between. This region is further divided in two subregions. One is between 0 and UF, and the other one is between UF and 2 UF, okay? So essentially we have 1, 2, 3, 4 regions, and 3 remarkable points. One remarkable point is 0, one is UF, and the other is 2 UF, okay? So at this point we can analyze better what happens in the semiconductor by considering separately the 4 regions and the 3 remarkable points. And we do it with the aid of the expressions of the charge, of the concentration, sorry, of the electrons and holes at the surface. You remember, we are in the equilibrium condition. And we assume the non-degeneracy condition. So the concentration of the electrons at each point of the semiconductor is NP0 times the exponential of Q phi over KT, or exponential of U if we are using the normalized variable. And similarly, the concentration of the holes at each point is PP0 times the exponential of minus U. In particular, we can calculate the values of the concentrations of the electrons and holes at the surface. And we shall call them NS and PS, okay? And of course, we calculate them from the exponentials by using phi s or US in the exponent, okay? Conclusion, the concentration of the electrons at the surface is N at 0, that is NP0 exponential of US, or if we consider the alternative expression that you remember is the intrinsic concentration times the exponential of US minus the normalized Fermi level. Similarly, PS is PP0 exponential of minus US equal to Ni exponential of the Fermi level, the normalized Fermi level, less U sub S, okay? So, the first zone, you remember, is for US negative. When US is negative, obviously, the concentration of the holes, since the exponential of minus US is positive and larger than 1, PS is larger than PP0, whereas NS is smaller than NP0. So when US is smaller than 0, we have a chain of inequalities showing that the surface concentration of the electrons is smaller than the asymptotic concentration of the electrons. That in turn is smaller than the, is smaller than the intrinsic concentration. That is smaller than the asymptotic concentration of the holes. That is smaller than the surface concentration of the holes. In conclusion, we have at the surface, in this condition, we have more holes than in the flat band condition, and more than the number that is present asymptotically in the bulk. Because of that, we call it accumulation condition. The second condition is flat band. At flat band, US is 0, that means that NS is equal to NP0, PS is equal to PP0. Obviously, the concentration of the holes is the same everywhere. The concentration of the electrons also is the same everywhere. Then we make US positive, but not that much, so that US is in between 0 and UF. At this point, it's convenient to consider the alternative expressions, okay, because US minus UF here is negative. That means that NS is smaller than NI, but at the same time, US is positive. So NS is larger than NP0. In turn, PS is larger than NI and PP0 is larger than PS. That means that when we apply a positive voltage to the gate such that US becomes positive, but not very positive, so it is between 0 and UF, the number of holes at the surface, PS, decreases with respect to the asymptotic value because the holes are pushed away from the surface. So there are not so many holes. The electrons increase, but they are still very few because their concentration at the surface is smaller than the surface concentration. So we have a region near the surface that is practically depleted of mobile charges because the holes are pushed away. The electrons are attracted, but there are not so many of them yet. If we keep increasing the voltage so that we bring US equal to UF, obviously from these last expressions we have that NS and PS become equal to NI. So at the surface, the concentrations of the electrons and holes are equal to each other and equal to the intrinsic concentration. So this is a situation that is similar to that of the intrinsic semiconductor. You remember in the intrinsic semiconductor, the two concentrations are everywhere equal to each other. Here they are equal only at the surface, okay? And you remember, in the intrinsic semiconductor, the Fermi level is at the mid-gap, okay? So this condition is called mid-gap. The surface is in a condition that is equivalent to that of the intrinsic semiconductor. If we keep increasing US, so that now US is in between UF and 2UF, it happens that the concentration of the electrons at the surface becomes larger than Ni, but still is smaller than PP0, whereas the concentration of the holes at the surface is smaller than Ni, still larger than NP0. You see that the relative concentrations of electrons and holes are, so to speak, inverted. The electrons that are the minority carriers, because we are in a p-doped semiconductor, have a surface concentration that is larger than that of the holes that are the majority carriers, okay? So this equation is called the weak inversion of the surface, okay? The electrons that are the minority carriers are more than the holes at the surface. Then, if we keep increasing, we reach the condition US equal to UF. At this point, the surface concentration of the electrons becomes equal to the asymptotic concentration of the holes, and vice versa, the surface concentration of the holes becomes equal to the asymptotic concentration of the electrons. So we call this condition threshold of the strong inversion. Finally, if we still increase the surface potential so that US becomes larger than 2UF, then the surface concentration of the electrons becomes larger than the asymptotic concentration of the holes. And conversely, the surface concentration of the holes becomes smaller than the surface concentration of the electrons. So in this case, the surface is called strongly inverted. We have a condition of strong inversion of the surface because not only the electrons are more in number than the holes, but they are also more than the asymptotic concentration of the majority currents that are the holes. So we stop and we shall resume in 10 minutes.
Okay, so after distinguishing all these functioning regimes of the MOS capacitor, we may exploit the approximation that we discussed earlier, okay? So you remember we have an exponential behavior for negative US, an exponential behavior again with when we are above the threshold of the strong inversion. And now that we know the names of the different regions, we have a behavior that is essentially proportional to the square root of the surface potential in the depletion and weak inversion conditions. Okay, so we have a charge that is essentially proportional to the square root of the surface potential here in this part of the curve. Okay, so let's try to express this relation in full. That is by taking the approximation and then reverting to the non-normalized quantities, okay? So what we do is we take, I go one page back for a second. We take the general expression, this one, QSC equal to minus or plus this coefficient time F. Then we observe that US is positive, so we have to take the minus sign. And then we use for F the approximation of the square root of the surface potential. In so doing, we obtain this expression here. Okay, so this is the approximate expression of the charge of the semiconductor per unit area that applies in the depletion and weak inversion conditions. That is when US is for a p-type substrate is between 0 and 2 UF, okay? At this point, we can simplify many things because if we make the expression of the Debye length explicit, okay, remember that the Debye length has the permittivity in it, the concentration of the holes asymptotically, the thermal voltage, many things. So when we express LA with its formula, we can simplify many things. So this expression here becomes much simpler, this one. It is equal to minus the square root of 2, the permittivity of the semiconductor, Q, PP0 phi S, okay? So we have a few constants and phi S. So we extract the square root of phi S, and then we are left with the constants that are the square root, it is visible here, of 2 permittivity Q PP0. At this point, for reasons that are not obvious but will become obvious very soon, we divide and multiply by the oxide capacitance per unit area, so that the old square root that appeared in the equation is divided by the capacitance, and this ratio is called gamma. Okay, so we make a replacement such that in mid-gap depletion, mid-gap and weak inversion conditions, the charge in the semiconductor is essentially proportional to the square root of the surface potential, and the constant are minus Cox gamma. Okay? We have a few figures that illustrate some of the regions that we discussed before. You remember, for instance, we mentioned accumulation. Accumulation occurs for a p-type substrate of the capacitor when phi s or us are negative. That means that in this case we have, in this diagram in which the positive orientation of the axis of the electric potential is downwards, we have that Vg prime and phi s go up in the figure with respect to the zero because they are negative. So the bending of the bands is upwards. Okay. In this case, you remember we are in the accumulation condition. That means that we have a concentration of holes near the surface that is larger than the concentration asymptotically. Okay. Instead, the electrons are few anyhow, but they're pushed away. So in this condition, what we have is a concentration of holes at the surface of the semiconductor that is compensated by a negative charge on the side of the metal. So this is accumulation. The next figure is the mid-gap condition. If you look carefully, you see that Vg prime is positive. So we have attracted electrons to the surface and we have pushed away the holes from the surface. And if you look at the figure, we have that phi s is exactly equal to phi f. This is what we call the mid-gap condition, and you see that the mid-gap here coincides exactly with the Fermi level of the material. Well, the Fermi level now has a distance from the edge EC of the conduction band that is exactly equal to the distance between the Fermi level again and the edge EV of the valence band. So the two distances are equal, and if you remember from the general expressions of the concentrations, that the concentration of the electrons at the surface is equal to the concentration of the holes at the surface, and both are equal to the intrinsic concentration. Of course, the intrinsic concentration is small. So the concentrations of electrons and holes at the surface and more generally in the depleted region are negligible. Okay, so if you look at the charges, in this case, the charge in the semiconductor is given essentially by the dopants. There is no concentration of electrons or holes of any importance near the surface. Okay, so in this case we have simply a depletion condition, and in fact, you remember the expression of the charge is proportional to the square root of the electric potential. We are in the mid-gap condition in the figure that we are discussing now. Finally, we go to this case in which Vg prime is positive and larger than in the previous figure, to the point that, you see, phi s is exactly equal to the double of phi f. So we are here in the at the threshold of the strong inversion. And you see the distance of the Fermi level from the edge of the conduction band is small. That means that we have many electrons. And the distance of the Fermi level from the edge of the valence band is large. That means that we have few holes. Okay. In this case, we do have a layer of electrons near the surface. Okay. All these considerations will be useful also when we consider the MOS transistor. Okay. But in the MOS transistor, when the surface is in the accumulation condition here, this means that essentially the channel of the MOS transistor is blocked, so there is no current through the channel. Okay, so the accumulation of the surface translated into the language of the MOS transistor indicates that the transistor is off. There is no current possible in the transistor. So for this reason, the condition of accumulation is not so important. Okay, whereas the important conditions are those related either to the depletion and weak inversion, like the one that is illustrated here, or the threshold of the strong inversion and the strong inversion condition. Okay, so these two situations differ because in the first one, we have only the charge of the semiconductor associated to the fixed dopant atoms and no layer. Whereas in the second situation, we have both the charge associated to the dopant atoms plus the layer of electrons. Okay, so if we want to consider together these two situations, we may think of setting up a simplified theory in which we exclude accumulation once and for all. And we want to incorporate into the theory only the depletion, weak inversion, and strong inversion condition. And we say, we express the charge of the semiconductor as the superposition of the charge due to the dopants plus the charge of the layer of electrons, if that layer exists. So if you are in the strong inversion condition. If the layer does not exist, we simply put it to 0. Okay? So we try to set up a general theory that is simpler than that used so far. Okay? But this simplified theory is yet very useful for the MOS transistor. Okay? And we try to avoid using the complicated relation with exponentials that we found by solving the Poisson equation, okay? So we go back to the definition of the semiconductor charge per unit area, that is the integral from 0 to infinity of the charge density, okay? And we take an approximation. We say, if we are in this condition, that is depletion or weak inversion, we don't have any layer of electrons. Okay, we consider only this charge. If instead we are at the threshold or in the strong inversion condition, we do have a layer, but we consider this layer as very thin so that we can approximate the layer with the Dirac delta. Okay, what is the advantage of doing that? Is that the Dirac delta has a zero thickness. Okay, so we can think of it as a sort of boundary condition near the interface. Okay, and consider the charge, only the charge associated to the dopants as a charge distributed over a volume of material. So, first of all, we take phi s positive. That means we are excluding accumulation from now on. Then we take the Ashe approximation. We say there is a position LP such that to the right of LP we have a neutral semiconductor. To the left we have a space charge. Okay, so we are using the Ashe approximation. That means that the charge density of this integral is considered as non-zero only between the origin, that is the interface, and LP, okay? Neglect this symbol XD, we shall come to it later, okay? So the integral becomes integral from 0 to LP only. So this is approximation number 2. Then we remember, since the electrons, if any, in the surface layer, and we call them minus Qn, and the negative ionized acceptors, and that concentration will be called minus QNA. Then we separate the integral, and we call QI, that is, I stands for inversion. The integral of minus Q of n in dx from 0 to LP if non-zero. The other part of the integral associated to Na will be called QB. B stands for bulk. This is the bulk charge. Qi and Qb, of course, are charges per unit area. Okay, and Qb is easily calculated because when we adopt the Ashe approximation, QB is simply the area of the rectangle, so that QB is minus QNA times LP. Okay. Next, the approximation for the charge of the layer will be a Dirac delta, okay? What is the advantage? We already mentioned that, is that if we consider the inversion layer as a Dirac delta, it is just a boundary condition. It is of zero thickness, okay? So in the rest of the volume between 0 and LP, the charge density is simply minus QNA, okay? So this is the point. This is where the simplification helps. If we have a constant charge between 0 and LP because we have squeezed this layer to the origin, okay? Solving the Poisson equation becomes obvious because we have the second derivative of the potential equal to a constant, okay? So this is where the simplification helps. We say the second derivative is equal to, remember, it is minus the charge density over the permittivity. So this renders QNA over epsilon SC between 0 and LP. And the boundary conditions, you remember, we have charge neutrality from LP on. So by continuity, we may state that at LP, the potential is 0 because we have set the 0 there. And the field is also 0 because the region beyond LP is equipotential. At this point, this second order equation is immediately solved. It gives you a parabola. So this is the form of the electric potential in the depleted region. By the way, it is qualitatively. This is a sort of parabola, okay? It's this solution, okay? Next, we can immediately derive a relation for the surface potential because the surface potential is the value of the electric potential at the point x equal to 0. So when we force x to be 0 in this expression, we obtain phi s. So phi s is proportional to the square of LP. Remember, LP is not given. LP is something that depends on the applied voltage, of course, okay? It's like the extension of the depleted region in a PN junction. You remember, it depends on the voltage, okay? But yet we are building up useful relations. At this point, we take the relation for QB from the Ashe approximation, this one. We extract LP from this one, and we replace it. You may observe that this expression is practically identical to the approximation that we obtained here, to this. Exactly the same. The only difference is a minor difference is that here we have PP0, in the other one we have NA, but they are practically equal as you remember, okay? So this relation applies in the depletion and weak inversion condition. We extend this relation also to strong inversion because we have replaced this layer of charge with the Dirac delta. Okay, so we have again a constant charge associated to the dopant atoms. Okay. Then we put all these ingredients together. Remember this, the total charge of the semiconductor per unit area is the sum of the inversion charge, if any, plus the bulk charge. We are excluding once and for all the accumulation regime. So QSC is equal to QI plus QB. In turn, QSC, that is the opposite of the charge on the metal, you remember, can be written as minus Cox times Vg prime minus phi s, which is fully general because it is obtained by solving the Poisson equation on the side of the metal, okay? But now we have another relation. QB is minus Cox gamma square root of phi s. So now we take Qi, the inversion charge. Of course, it is the difference of QSC minus QB. We extract Cox, and we have this expression. So this expression is able to provide a relation connecting the surface potential here with the inversion charge when we exclude accumulation, okay? It is not able to give us independently Qi and phi s because we have been introducing approximations, okay? So this is not possible anymore. If we wanted to calculate phi s and all the other things, we should take the general solution of the Poisson equation that we found earlier, okay? But this expression is fundamental because it is the fundamental relation that is then applied, as we shall see very soon, in the calculation of the current of the MOS transistor. So this is very important. You should memorize it, okay? Of course, the quantities are such that the brackets is positive, okay? So this is negative because of the minus sign, and it is correct that it must be negative because Qi is a charge due to electrons. So it is negative for the p-type substrate, okay? Then, if we are in the strong inversion condition or at the threshold of the strong inversion condition, Qi is non-zero. If Vg prime is smaller than the one that reaches the threshold, then phi s will also be smaller, and the brackets will go to 0. So when phi s is in between 0 and 2 phi f, that is in the depletion or weak inversion condition, the difference between this first block in brackets, Vg prime minus phi s, and the other block, gamma square root of phi s, is negligible. These two quantities are almost equal. And the inversion charge, Qi, is negligible. Okay, so this is the important expression that we have found with some approximation that are more or less acceptable. I mean, they work quite well for the basic theory of the MOS transistor. Now we come to another issue, which also has similarities with the PN junction. The MOS capacitor is a structure in which there is no current, and in which we have on one side of the dielectric, we have some charge, in the metal, for instance. And on the other side, in the semiconductor, we have an equal and opposite charge. So again, the MOS capacitor is a capacitor, of course. But again, it is non-linear, okay? So we may associate a capacitance to it, but it must be a differential capacitance, okay? So we must, as just we did, just as we did in the PN junction, we have to take the derivative of the charge with respect to the gate voltage. So we calculate now the differential capacitance of the MOS capacitor. Since we are using charges per unit area, we shall obtain a capacitance per unit area. You remember, we must take the variation of charge on the same contact as the contact where we have the variation of voltage. Okay, so since we commonly take the bulk contact as ground, the variation of the voltage will occur at the gate contact, and we have to take the change in the charge at the same contact. So we take the variation of Qm. So by definition, the capacitance per unit area of the MOS capacitor is the derivative of Qm with respect to Vg, but Vg differs from Vg prime by a constant, so we can take dQm over dVg prime. And the calculations are easier if we consider the inverse. So we calculate the inverse of C. So we calculate, as you see on the second line, dVg prime over the Qm, okay? We simply adjust the numerator by, we add d phi s and we subtract d phi s, okay? And then we remember that Qm can be expressed as Cox times Vg prime minus phi s. So the first part of this fraction is simply 1 over Cox, okay? The second fraction is d phi s over dQm, but Qm is minus QSC, okay? So we have to define the second fraction here. So we introduce a capacitance per unit area that is called CSC. It is the semiconductor capacitance per unit area. We define it with a minus because we have a minus in the original formula, okay? Then with some manipulation, we can replace phi s with kT over Q times US. We denormalize the surface potential. And then we observe that we already have found the expression of QSC in terms of US. It is the general expression with no approximations, okay? This one. QSC is a function of US. So we simply take the derivative, okay? And we call this the semiconductor capacitance per unit area, okay? Again, we have the double sign because F has a double sign in it. However, from the discussion that we had, it turns out that this capacitance is always positive, okay? Which is reasonable because if you, for instance, increase US, okay, the charge becomes in the semiconductor more negative because when you increase US, you are attracting electrons, okay? So DUS is positive and the differential of QSC is negative, but you have a minus sign. And you can check all combinations and you see that CSC will always be positive, okay? So in conclusion, the inverse of the differential capacitance of the MOS capacitor is the sum of two blocks. One is a constant. It's simply 1 over the oxide capacitance per unit area, and the other one is the inverse of CSC, and this is a function of the applied voltage. Okay, so as expected, the capacitance depends on the voltage, so it is a nonlinear capacitor. Also, you may notice that when the inverse of a capacitance is the sum of the inverses of two individual capacitances, that means that the two individual capacitances are placed in series to each other. So the MOS capacitor is the series of a constant capacitance due to the oxide and of a non-constant capacitance due to the semiconductor. It is also easy to calculate there must be some figures somewhere. Okay, they are too far away. We shall find them later. We have only a few minutes left. And it is convenient to devote these few minutes to this problem. All the theory of the MOS capacitor so far has been considered in the static situation. Simply, we assume that the applied voltage is a constant. The gate voltage is a constant with respect to time. When we calculate the capacitance, of course, we have to change the voltage by a small quantity, but we do it statically. So we detect the charge with some Vg, and then we change Vg. We wait until all the transients have expired, and then we detect the charge again. But you know very well that in electronic circuits, typically the transistors, the MOS transistors that form an integrated circuit are or may be operated by pulses. Okay, in a digital circuit, you typically apply pulses to the transistor such that a transistor that is initially off receives a pulse that brings it to a condition that is above threshold. So it starts being active almost immediately, okay? So what happens in dynamic conditions, okay? So let's assume a situation, a simple situation in which we have initially an MOS capacitor in the flat band condition. That is, potential is constant everywhere in the structure, and we have zero charge on the gate, okay? And then assume that the gate voltage is suddenly brought to a very large value that would correspond in static situation to the strong inversion regime, okay? So what happens in the semiconductor? What happens is very simply described. When you apply a large positive pulse to the gate of a transistor or to a gate of a capacitor whose substrate is of the p-type, you push away the holes. And this action is almost immediate, it's almost in no time, okay? Almost in zero time, because the time constants of this phenomenon are very short, okay? So you create almost immediately at the application of the positive pulse a region that is fully depleted because I pushed away the holes and there are very few electrons, okay? You do not have immediately an inverted layer. Why? Because the inverted layer takes time to form. Essentially, when you deplete a region, you remember the generation recombination mechanisms, okay? When a region is depleted and there is a lack of mobile carriers, the semiconductor starts generating electron hole pairs, okay? So the electron hole pairs that are generated in the depleted region are immersed in a very strong electric field, such that in this example, the holes are pushed to the substrate, whereas the electrons are attracted to the surface and they form the inversion layer, okay? Only at the end of a transient during which the inversion layer is formed, only in that case, the transient stops and you have a static situation corresponding to strong inversion, okay? But before that, during the transient, the inversion charge is small with respect to the asymptotic condition. Because of that, you can still apply the expression that we found, because this expression was found essentially by solving the Poisson equation, so it is generally correct, okay? But in this expression, we have that Qi is not the full inversion charge that we have in static condition. Its modulus is smaller during the transient. Actually, initially it is zero, okay? Conclusion, we may calculate a relation in which we extract the potential, the surface potential phi s, as a function of the charge per unit area of the inversion layer. We can still do this, okay? So let's do it. You see, we can manipulate this expression by bringing Vg prime to the left, and we define Vi equal to Vg prime plus Qi over Cox, okay? So this expression becomes this, okay? This is a very simple second order equation whose unknown, second degree algebraic equation, sorry, whose unknown is the square root of phi s, okay? So you find phi s as a function of the existing charge in the inversion layer, okay? As I said before, we are applying a pulse. At the instant of the pulse, Qi is 0, okay? Qi is 0. So we go to the next page. We have an expression for the surface potential in which Vi is given by this, okay? So look, when Qi is 0, Vi is the largest. When Qi reaches the asymptotic value in time, so when the inversion layer is fully formed, this modulus of Qi is, of course, some positive quantity, and Vi is minimum. So phi s starts very high, and then during the transient goes to the asymptotic value corresponding to the steady state condition. So in practice, when we apply a pulse to the gate of the MOS capacitor, we open up a very large depleted region, and we do not have initially an inversion layer. This is fundamental for optical sensors because we may try to exploit the presence of a very large depleted region quickly in order to detect some light that comes into the semiconductor before the thermal generations fill up the inversion layer. So this is, of course, a purely qualitative description, but we shall see very soon that this is a fundamental operation that is used in practice for implementing a class of optical sensors. This is some quantitative relation, but I think we can leave them for Tuesday. So we may stop here. There are still 2 minutes left, so if you have any questions, you may ask them. And if there are no questions, I thank you, and we meet each other again on Tuesday.